Have you ever stopped and wondered what's actually holding together a massive app like Gmail or your entire online banking system? It's not magic, even though it can feel like it. It's architecture. And today, we're going to pull back the curtain and look at the hidden blueprints that make our whole digital world tick.
To get our heads around this, let's start with a really simple analogy. On the left, you've got a skeleton. That's the actual physical structure, right? And on the right, you have an X-ray. Now, the X-ray isn't the skeleton itself. It's a representation, a specific way of looking at that structure. One is the real deal, the other is the blueprint. And you need both, but for totally different reasons.
So, in the software world, that skeleton, we call that the architectural structure. It's the real thing. It's the actual set of components, the code, how everything is organized and running on the hardware. It's the guts of the machine.
And the X-ray? Well, that's what we call an architectural view. It's not the system itself, but it's the blueprint, the diagram that we, the stakeholders, the developers, the managers use to understand, discuss, and analyze that underlying structure. An architect's job is really to create these different X-rays to show the system from all the important angles.
So, here's our game plan for this explainer. We're going to unpack the architect's toolkit, starting with the three main categories of structures. Then we'll dive into some key examples from each one. And finally, we'll connect it all back to why having these different blueprints is so absolutely critical.
All right, let's crack open that toolkit. You'll find that pretty much every single software blueprint out there falls into one of three fundamental categories. And each one, well, it tells a completely different story about the system.
And this right here is our road map. You can see the three big families: module structures, component and connector structures, and allocation structures. We're going to tackle them one by one. So let's jump right into that first one, modules.
Okay, so module structures. This is all about the code itself before it's even running. Think of it like how the source code files are organized on a developer's computer. Getting this part right is absolutely key for making the software easy to change and maintain later on without causing a total disaster.
The most basic and honestly the most important type here is the decomposition structure. You just take a massive, complicated problem and you do what people have always done. You break it down into smaller, more manageable pieces. You keep breaking it down until each little part is simple enough to understand and actually build.
And this visualizes that process perfectly. You've got this giant member services system at the top, way too big to tackle at once. So you break it down into things like subscription and order. Then you break those down even further. See, this isn't just a pretty picture, it's a battle plan for how the team is going to build this thing without getting lost in the complexity. Now let's talk about another key module structure, the layered pattern. Here, you organize modules into stacks, kind of like a cake, and there's one simple rule: a layer can only use the services from the layer directly underneath it. This keeps things incredibly clean and means you can swap out an entire layer, like your database, without breaking everything above it.
Just think about Gmail. They don't have to build a whole new version of the app for every single language, do they? Of course not. Instead, they have a user interface layer that handles all the language-specific stuff. Under that, there's a core processing layer that does all the heavy lifting with emails, and at the bottom, a database layer just for storage. Because these layers are separate, the whole system is incredibly flexible.
All right, let's move on to our second category, component and connector structures. Now, if module structures are about the static code, this is about the living, breathing system when it's actually running. It describes the pieces of the puzzle that are actually executing, and more importantly, how they're all talking to each other while you're using the app. A really popular way to do this is with the service structure. The whole idea here is to create components that are like little black boxes. They offer a specific service, like processing a payment, and any other application can use it without having to know a single thing about how it works on the inside. This is a fantastic, real-world example of that. Imagine you have some old internal financial system from the 90s. It's got valuable data, but it's totally locked down. So what do? You build an exposed service that acts as a modern translator. It allows brand new web and mobile apps to talk to that old system securely and efficiently. It's a genius move. Another crucial runtime idea is concurrency. This is when your computer seems to be doing a bunch of things at once. And the key word there is seems. Even if you only have a single CPU, it can switch between tasks so incredibly fast, I'm talking nanoseconds, that it creates this perfect illusion that it's all happening at the same time.
And this slide illustrates the difference perfectly. On the left, concurrency is like one person juggling multiple balls.
It looks like everything's in the air at once, but really they're just switching their attention super fast. On the right, you have parallelism. That's totally different. That's when you take a big job, break it into pieces, and have multiple people, or multiple CPUs, working on the pieces at the exact same time. It's true simultaneous action.
And that brings us to our third and final category, allocation structures. This is where the digital world meets the physical world. It's all about how the software connects to hardware, to networks, to file systems, and yep, even to the people who are building it. This stuff directly impacts things like cost, security, and how resilient the system is.
The classic blueprint for this is the deployment structure. You can think of it as a map that shows exactly which piece of software lives on which physical server and how all those servers are connected to each other over the network.
Take a look at this diagram. It lays it all out. You can see the FTP and mail server software is living on one physical machine. The DNS server is on another one. They communicate over a trusted, secure network, which then connects out to the mainframe and the internet. This kind of view is absolutely essential for figuring out performance, security, and reliability.
But allocation isn't just about hardware. It's also about people. This is a work assignment structure. It maps software modules to the actual human teams that are responsible for building them. And this is so critical because it defines the communication paths between people, not just servers. It tells you who owns what, which helps avoid organizational chaos.
So after all that, we finally arrived at the big question. Why? Why do architects need so many different blueprints for the exact same system? And the answer, really, is all about achieving quality.
It's because each type of blueprint is a different tool for a different job. If you want to make sure the system is easy to change and update down the road, you focus on the module structures. If you need to squeeze out every last bit of performance, you're going to look at the concurrency structure. And if you're worried about security or making sure the system doesn't crash, that's a job for the deployment structure. You choose the right blueprint for the problem you're trying to solve.
So the next time you tap an icon on your phone and an app just springs to life, remember what's going on beneath that simple surface. There's this complex, invisible world of structures and views, all carefully designed. And it makes you wonder, right? What complex blueprints are holding it all together?